Jnanam paramam dheyam. Knowledge is supreme.
So now we will look at how a second order system reacts to a simple disturbance like a step input, and that will also help us classify these second order dynamical systems, and we will see why that classification comes about and how it is related to the parameters of a second order dynamical system. So we will now look at step response for second order dynamical system. So we will work with a general transfer function of a second order system, which is Kp over tau square s square plus twice zeta tau s plus 1, which is equal to ys over us. And we are looking at step response. So the transfer function of the input is going to be a over s, where a is the step size. So you can write that the Laplace of output y is going to be gs times us, which will be akp over s tau square s square plus twice zeta tau s plus 1. And in order to fraction this denominator, we will also divide everywhere numerator and denominator by tau square. So we have akp over tau square s square plus twice zeta over tau s plus 1 over tau square. Now in order to get the response of yt from this Laplace transform, we will be using the method of partial fractions. So for that we will have to decompose this term into its factors. So to do that, what we would be doing is we will be writing this as ys is equal to akp over tau square s minus p1 s minus p2, and this p12 will be given by the factors of this particular polynomial, which would be minus zeta over tau. So we will be writing minus b plus minus root beta square minus 4ac over 2. So the 2p12 can be given by minus zeta over tau plus minus root of zeta square minus 1 over tau. So now you can see that we can have three possibilities here. Possibility 1 is if zeta is going to be greater than 1, in that case what we will have is this term will be less than the first term, and in that case we will have two distinct roots which will be real. So the partial fraction would be 1 over s, the partial fraction would be a over s plus b over s minus p1 plus c over s minus p2. So there will be three different exponential, one constant term, one e raised to p1 and other e raised to p2 terms. When we look at zeta equal to 1, however, in that case this term will go away and all our both the roots are identical. So in that case we cannot directly write as a over s plus b over p1 plus c over p2. We will have to use the square term as well, and in that case the response would have. So if I write down the type of responses we are going to get, here we will have a constant e raised to p1t and e raised to p2t. In this case what we will have is a constant e raised to power p1t and t e raised to p1t. So these will be sort of different types of dynamics, slightly different dynamics. And then the last case is if zeta is less than 1, in that case this will be square root of a negative term. So what we will have is a complex conjugate root. So this is going to give rise to sinusoids. So depending on the value of zeta, we may have simple constant and exponents, we may have constant exponent and some time multiplied by exponent, or we can even have sinusoids. So this damping coefficient essentially gives different sorts of dynamics depending on its value compared to 1, and this kind of gives the classification of a second order dynamical system. So depending on value of zeta to be greater than 1, equal to 1 or less than 1, we have three different types of second order dynamical systems, and we will be discussing these further after a short break. Thank you. Hello students, welcome back. We are looking at a response of a second order system to a step input, and based on that we will be getting the classification of second order systems. So the transfer function for the second order system in a generic form is Kp over tau square s square plus twice zeta tau s plus 1, which is equal to ys over us, and as we are talking about a step response, us will be equal to a over s. So accordingly we will get the Laplace form of the output response as akp over tau square s square plus twice zeta tau s plus 1, and we will try to write it in the form akp times 1 over tau square s square plus twice zeta over tau s plus 1, wherein we can, this ys will be s, so that we can write it or expand it in terms of partial fractions as some constant a over s plus b over s minus p1 plus c over s minus p2, wherein p1 and p2 are the roots of this equation s square plus twice zeta over tau s plus 1, and we had seen last time that depending on the nature of these roots we will get different types of dynamics. So let us consider the first case when we have zeta greater than 1. So in that case you will get real and distinct roots, where these p12 are equal to minus zeta over tau plus minus root zeta square minus 1 over tau. So in that case, what we get as ys as akp a over s plus b over s minus p1 plus c over s minus p2. This will be equal to akp 1 over tau square over the same denominator which we had earlier, s square plus twice zeta over tau s plus 1. So we can use method of partial fractions to obtain the values of a, b and c. So for this system what we get is a equal to 1, b will be equal to 1 over 2 root zeta square minus 1 root of zeta square minus 1 minus zeta, and c similarly will be equal to 1 over 2 root zeta square minus 1 root of zeta square minus 1 plus zeta. So accordingly, when we substitute these, we are going to get a response of the form. So when we take inverse Laplace, we will get y of t is equal to akp, and then inverse of 1 over s will be a constant 1, and then we will get b times e raised to p1t plus c times e raised to p2t. Now here we can do a lot of algebraic manipulations, rearrangements, and then eventually we can simplify this system. So I will skip few steps and I can show you that the response would look like 1 plus, we can write these terms, 1 over 2 root zeta square minus 1 root of zeta square minus 1 minus zeta times e raised to power minus zeta over tau plus root of zeta square minus 1 over tau t plus 1 over 2 root zeta square minus 1 root of zeta square minus 1 plus zeta times e raised to power minus zeta over tau minus root of zeta square minus 1 over tau t. So I will not show each and every step of this simplification, but I will give you some guidelines about how you can proceed. The first thing is you can take this term common. The next step would be will be expanding these as e raised to minus zeta t over tau and e raised times e raised to root of zeta square minus 1 t over tau. Similarly, we can expand this as e raised to minus zeta t over tau divided by e raised to root zeta square minus 1 t over tau, and then again you can notice that these terms will be common. So we can take these common as well. So we will be left with this term with this in the denominator, and we will be leaving with this term with this in the denominator, and then later on we can just do the addition. It will be a minus b, a plus b. So denominator again will be zeta square minus 1 minus zeta square. So again the denominator of the resulting addition will be minus 1. So this plus would become minus 1. So once you do all these simplifications, what you would end up with will be y of t is equal to akp 1 minus e raised to minus zeta t over tau over 2 root zeta square minus 1 So, you will be left with this, and again what we can notice now is which we can now simplify again as yt is equal to akp 1 minus e raised to minus zeta t over tau, and we will take the remaining thing inside. So, in this case you can observe that we have this root of zeta square minus 1 common in both the sides, and then it will get cancelled with this root of zeta square minus 1. So, what we would eventually left with will be e raised to power root zeta square minus 1 t over tau plus e raised to minus root zeta square minus 1 t over tau over 2. And similarly, for the other case what we would have is zeta over root of zeta square minus 1, and then it will be the other term which will be e raised to root of zeta square minus 1 t over tau minus e raised to minus root of zeta square minus 1 t over tau, and this will be divided by 2, which we can note that this will be a cosine hyperbolic form and this other thing is sine hyperbolic. So, the final response of this system will be given as yt is equal to akp 1 minus e raised to minus zeta t over tau cosine hyperbolic of root of zeta square minus 1 t over tau plus zeta over root of zeta square minus 1 sine hyperbolic of the same term zeta square minus 1 t over tau. So, you can note that the response of a second order system when zeta is greater than 1 would be given by this term which has the overall multiplication factor of akp, and you can very well appreciate that that akp would eventually lead you to the final value of the response. So, when t goes to infinity this entire term will go to 1, or this entire term will vanish. So, as t tends to infinity this entire term would go to 0 because there is a decaying exponential. This is I am talking about the case when zeta is indeed greater than 0, and the final value of the response would then be given by akp. I would show the response of this system in some time when we have looked at all the other criteria in terms of the values of zeta. So, for now this is the response when we have zeta greater than 1, which is also known as an overdamped response, and I will also show you why it is called as overdamped response when we look at the other two cases as well. So, the second case is when zeta is indeed equal to 1. In that case we get real and identical roots, which will be p12 will be equal to minus 1 over tau. So, in that case as we have a double root we will have to use a slightly different version of partial fractions. So, what we would be writing as y of s will be akp, which we have is 1 over tau square s square plus 2 over tau s plus 1 over tau square. This is we are going to write as akp constant a over s plus b over s minus p plus the double root which is s minus p square. So, in this case when we use partial fractions what you are going to end up with is a equal to 1, b will come out to be equal to minus 1 and C will come out to be minus 1 over tau. So, when we substitute this, we will get Ys is equal to AKP 1 over S minus 1 over S plus 1 over tau minus 1 over tau S plus 1 over tau square. And now we can take a Laplace inverse for this. To get y of t, which will be AKP, Laplace inverse of 1 over s would be a constant 1, and then Laplace inverse of 1 over s plus 1 over tau will be an exponential term, so minus e raised to minus t over tau, and the last term is minus 1 over tau, 1 over s plus 1 over tau square. So, it is like the inverse of that will be t times e raised to minus t over tau, which we can condense and write as AKP 1 minus e raised to minus t over tau 1 plus t over tau. You can see that the form of the response is similar to the response for the case when zeta was greater than 1. So, this is for zeta equal to 1. So, we have still the first ultimate value as AKP. So, even this response, the final value of the will reach AKP. We have 1 minus e raised to a decaying exponential term e raised to minus t over tau, followed by a term which is a little bit simpler. In this case, there are no cosine, hyperbolic or sine functions. We have a simple linear function as 1 over t plus tau. So, this is the case when zeta is equal to 1, which we also call as critically damped, and we are one step from coming to the origin of these terms as overdamped or critically damped, and we will consider the last case when zeta is indeed less than 1. So, in that case, what we have is complex conjugate roots. So, we have Ys as AKP 1 over tau square s square plus twice zeta over tau s plus 1 over tau square. This we are going to write in this case as AKP A over S plus Bs plus C over S square plus twice zeta over tau S plus 1 over tau square. So, for this case, the method of partial fractions would give us A will be equal to 1, B will come out to be minus 1, and C will come out to be minus twice zeta over tau. So, substituting these values, what we are going to get is y of s is AKP 1 over s minus s plus 2 zeta over tau over s square plus twice zeta over tau s plus 1 over tau square. Now, again I will not show you all the steps of this derivation, but what we are going to write is we are going to write this as s plus a square plus b square. So, we will write it as denominator as s plus zeta over tau square plus root of 1 minus zeta over tau square, and the numerator we will try to write it as, so this is for the denominator, and the numerator will split as s plus zeta over tau, which is similar to this, and the other term we will try to write in terms of this root of zeta 1 minus zeta square over tau. So that we will write as plus this remaining zeta over tau, we will write as zeta over root of 1 minus zeta square times root of 1 minus zeta square over tau. So the idea is we are going to get one factor which is same as this and the other factor which will give me this. So based on this, the way we will write this entire expression as ys is equal to akp 1 over s minus s plus zeta over tau over s plus zeta over tau square plus root of 1 minus zeta square over tau minus zeta over root of 1 minus zeta square root of 1 minus zeta square over tau s plus zeta over tau square plus root of 1 minus zeta over tau square. So essentially what we have written it as s plus a over s plus a square plus omega square, and this we have written as omega over s plus a square plus omega square. So this is going to give us so the inverse of this would be of the form e raised to minus zeta t over tau cosine of root of 1 minus zeta square t over tau, and inverse of this term is going to give me e raised to minus zeta t over tau sine of the same angle 1 minus zeta square t over tau. So now we know inverses of each of these terms, so we can finally take the inverse Laplace. So y of t would be equal to akp 1 minus e raised to minus zeta t over tau, which we are going to take common. We will have cosine of root of 1 minus zeta square t over tau plus zeta over root of 1 minus zeta square sine of root 1 minus zeta square t over tau, which we can further simplify as akp 1 minus e raised to minus zeta t over tau, and we will take this 1 minus zeta square out. So what we are going to have is root of 1 minus zeta square cosine of this angle plus zeta into sine of this angle, where I am simply writing this as star. And at this point what we would try to say is we will take some angle phi and we will say as zeta is less than 1, root of 1 minus zeta square is also less than 1. So we will call it a sine of some angle phi, and this zeta we will call as the cosine of the same angle phi. And this definition of sine and cosine is possible as long as we satisfy the identity sine square phi plus cos square phi equal to 1, which indeed is satisfied here. So that phi is equal to tan inverse of root of 1 minus zeta square over zeta. So this becomes sine a cos b plus cos a sine b, which ultimately the final form of the response will be sine of a plus b, and the final response we are going to get out of this is yt is akp. You will notice that it also has a similar form of akp e raised to minus zeta t over tau root of 1 minus zeta square sine of root of 1 minus zeta square t over tau plus phi. So, this is the response of the system, second order system, when zeta is less than 1 for a unit step change. And now here you can see that we have the ultimate value, which is AKP, we have this constant, we also have an exponential decaying function. But what makes this response interesting is the presence of a periodic function, a sinusoid. So, we are going to have oscillations inside this system. So, that is essentially a characteristic of a second order or even higher order system, which was not at all present in a first order system. So, this second order system can oscillate even though input does not oscillate. So, this was not possible in a first order system. When we talked about a first order system, if we give a sinusoidal input, you will get sinusoid at the output. So, if you oscillate the input, the output will oscillate, but when the input was constant, then the output would never oscillate. Not the case with the second order system. So, when zeta is less than 1, even though we have made a step change, the output is going to oscillate, and what we would actually see is, so when we say this coefficient is equal to 0, in that case we will get the response which is of the form yt is equal to AKP 1 minus sine of t over tau plus phi, which in this case will be 0, which in this case will be infinity, or pi by 2, tan will be infinity. So, what we are going to see is sustained oscillation. So, the output is a pure sinusoidal, and then it is continuously oscillate with this radian frequency of 1 over tau, and as we start adding or increasing value of zeta, these oscillations would reduce or decay in time, because we are going to add contribution to this decay factor of e raised to minus zeta t over tau, which multiplies the sinusoid. So, as zeta keeps on increasing from 0, the contribution of this, so the contribution of the sinusoid will keep on reducing, and this will happen till we have zeta equal to 1. So, in that case there are no oscillations. We had seen this case when zeta was equal to 1, the response did not contain any sinusoid, it was a pure linear function in that curly bracket. So, what we are going to see is, as we are increasing the value of this parameter zeta, we are going to dampen the oscillations. So, that is why this zeta was also known as a damping coefficient. So, it is damping the oscillations, and that the genesis of this name damping coefficient, and this damping is 0 when we do not have any value to this. So, when the value is 0, there is no damping to the oscillation, we get sustained oscillations, and as we start increasing the value from 0 to 1, we are progressively going to dampen these oscillations, but this damping is not complete. So, not complete damping of oscillation when we are between 0 to 1, that is why it is known as under damping. When we reach the value of 1, all the oscillations, that is the minimum value of zeta which is required to dampen all the oscillations, that is why this case is known as critically damped. And lastly, when we go for a value greater than 1, in that case there are no oscillations to dampen. So, we have already dampened all the oscillations, we are unnecessarily over damping the system, that is why when zeta is greater than 1, we call it as an over damped system. So that is the genesis of the name damping coefficient, and also the classification of the second order systems based on the value of this damping coefficient. If the value is between 0 and 1, we call it as an underdamped system. When the value is equal to 1, we call it a critically damped system, and when the value is greater than 1, we call it as overdamped system. So we will take a short pause here, and after that we will try to look at the example of that manometer and how it performs under these different cases of damping coefficient, and as well as we will look at some of the characteristics of this second order response. Thank you.